All right, everybody, this is the beginning of chapter 12. You're going to need out your paper and a periodic table, something to write with, obviously, and you're going to need a calculator. Again, it could be a calculator on your phone. It does not have to be a regular calculator, as long as you can do all of the problems. Most of it will involve just regular numbers. There might be the occasional scientific notation that you're going to have to do. Okay. All right. So chapter 12, how is this related to what we were doing in chapter 10? Well, we're still working with moles. That's still happening. We're still working with the idea that moles can be converted into grams, or moles can be converted into atoms or molecules, or moles can be converted into liters. All right, those were the three conversion factors that we had talked about before. The difference now is, instead of just working with one compound at a time, now we're going to be working with balanced chemical equations as a whole. Right? Back in chapter 11, we had talked about how to write chemical equations and how to balance them. Well, now we're going to really use those and actually going to do something with them. Okay? So this idea of stoichiometry, remember this is the word that we used at the beginning of this whole unit. Stoichiometry is the calculation of quantities. That's what we've been doing. We've been talking about how many in moles, or how much in grams, or how much in liters, or whatever it is. All right, except that specifically stoichiometry refers to balanced chemical equations. So we're really getting into the heart of stoichiometry here in chapter 12. All right, so this is our, for lack of a better term, our form of bookkeeping. Right, so that allows us to keep track of how much are we starting with, how much are we ending with. And remember, law of conservation of mass says that the mass that you put in has to equal the mass you get out at the end. So one of our jobs here is to go through and make sure we understand that if we change something at the beginning of a reaction, it's going to change something at the end of the reaction, right? If you were to go through and make a recipe, like it says here on the screen, right? It says if you were to make cookies from a recipe, and the recipe says that it makes 2 dozen cookies, but you want to make 4 dozen cookies. Well, it's really easy. If you want to make double the amount of product, the cookies, then you'll have to double all of the reactants, the ingredients that you put in at the beginning. A chemical reaction is no different. Right? We just want to keep track of how much does it take to put in at the beginning, how much do we get out at the end, and if we need to double something or cut something in half, we have to do it to all of the reactants and products. So what we're going to do here is we're going to learn how to interpret a chemical equation, because remember, a balanced chemical equation doesn't have any units in it. It just has numbers. We need to understand what those numbers mean. Okay, so I've taken this example from your book. I think this is a good example because it shows you lots of different ways that you can interpret a chemical equation, so you understand how it reads in terms of amounts. So you notice at the very top here, the very top of this page, it says that our chemical reaction is N2 gas plus 3H2 gas yields 2 NH3 gas. Right? That's our balanced chemical equation. So if you want to visualize it, they do that the next line down. They visualize it right underneath there. So they show you that if you had one N2 molecule, one nitrogen molecule, so that's those double blue blobs that are together, right? And then we have 3 H2, so 3 hydrogen gas molecules. So those are those 3 white molecules. If they were to all collide together, they would end up creating 2 NH3s, right? 2 ammonias. Remember, NH3 is called ammonia. So we have N2, so we've got 2 atoms of N. We have 3 H2, so that's 6 atoms of H. And when we're done, notice we still have the same number of atoms, right? We have 2 atoms of N, we have 6 atoms of H. So atoms always is conserved. However many atoms you put in at the beginning of the reaction has to equal the atoms that you get at the end of the reaction. That can't change. Now, molecules does not conserve. You notice if you look at this in terms of full molecules, 1 molecule of N2 and 3 molecules of H2 makes 2 molecules of NH3. So how many molecules you start with does not have to equal the number of molecules you end with. Atoms has to equal, but molecules don't. Now let's say we wanted to look at this in terms of moles. Well, remember, a mole is just 6.02 times 10 to the 23rd of that thing. So if this balanced equation says if we took 1 molecule of N2 and 3 molecules of H2, we'd make 2 molecules of NH3. Well, if you multiplied all of those by 6.02 times 10 to the 23rd, you would still have a ratio of 1 to 3 to 2. But now we can just think of it in terms of moles instead of individual molecules. Now, why is that important? Because you're never going to work with 1 molecule or 2 molecules or 3 molecules at a time. They're way too small. Nobody works with just that number of them. So in real life, if we're going to actually do anything with nitrogen or hydrogen or ammonia, we're probably going to be working with full moles at a time. So thinking of those coefficients out in front. Remember, the coefficients out in front are the big numbers that are out in front. So the number that's right here, so that's a 1 because there's nothing showing there. The number that's right here, that's a 3. And the number that's right here, that's a 2. Those numbers can be referred to as moles. All right, so we have our first really important way of describing or interpreting this reaction. This reaction says that if I take 1 mole of N2 and I take 3 moles of H2, I will make 2 moles of NH3. Okay, that's really important. That's probably the way that we're going to look at these chemical equations most of the time. We're going to think of those coefficients as telling us how many moles to take. Now, one problem with that is that if you actually were to go into the lab and you wanted to measure out moles, it's impossible to do. Remember, moles is just a number. Well, a number has to be counted. I can't count that high. I can't even see the individual atoms or molecules to count them anyways. So going strictly by moles is not going to be really useful. So at some point, we may want to change that to grams. Okay, we know how to change moles to grams. How do you change moles to grams? You have to use the periodic table, right? The periodic table tells us how to change moles into grams because it says the molar mass of each of the elements of the periodic table. Well, if you look up nitrogen on the periodic table, N, on your periodic table, if you're staring at it right now in front of you, and you should be, N says 14.01 or something close to that probably on your periodic table. So it's about 14 for one N. Well, if you have 2 N's, they weigh 28. So there's 28 grams of N2 in 1 mole of N2. Now, it's not going to say 28 up here in the balanced equation. It's just going to tell you 1 for moles. You can figure out how many grams that is, however, because you'll always have a periodic table sitting in front of you, so you can look it up. Same thing with the H2, right? How do we figure out how many grams of H2 are in 3 moles of H2? Well, an H weighs about 1 gram on your periodic table, right? It's 1.008 or 1.0079 or whichever, whatever you're looking at. So H weighs about 1 gram. So that means that H2 weighs about 2 grams. You're multiplying it by 3 because you have 3 moles of H2. So 3 times 2 is 6. So you have 6 grams of H2. So if you measured out 6 grams of H2, that would work pretty well because then you'd know that you had 3 moles of it. And then on the other side, it said 2 moles of NH3. So again, we'd have to change moles into grams. How do we do that? We would have to look up an N and 3 H's on the periodic table and add all of those molar masses up. So an N weighs about 14, an H weighs about 1. So there's 3 H's, so that's 3. So 14 plus 3 is 17. So NH3 weighs 17 grams. But we have 2 moles of it, which means 2 times 17 tells us we have 34 grams of ammonia. And remember, law of conservation of mass, right? Law of conservation of mass says, what's going on? There we go. Law of conservation of mass says that whatever grams, because that's mass, right? Whatever grams we put in at the beginning has to equal the grams that we get out at the end. And they do, right? They add up to be 34 equals 34. The last thing we could do, depending on what kind of reaction we're talking about, is we could convert that into liters. Remember, liters of a gas, this only works for gases, liters of a gas, assuming the gas is at standard temperature and pressure, STP, is 22.4 liters in a mole. So if you have 1 mole of N2, that means you'd need 22.4 liters of N2. If you have 3 moles of H2, then you need 3 times 22.4, which is 67.2 liters of H2. And then finally, you would make 2 moles of NH3. NH3 is a gas also, so you could think of it as 22.4 liters. But you have 2 moles, so 2 times 22.4 gives you 44.8. Notice these do not conserve. They do not add up. Liters is not conserved. Molecules is not conserved. The only thing that's conserved, right, is atoms and grams, right? Those are the only 2 things that are conserved. Mass and atoms. All right, so now out of all of this, what do you need to take away from it? You need to remember that when you look at a balanced chemical equation, the coefficients, the numbers up here in front of each of these, they stand for moles. That's what those numbers actually stand for. If somebody wanted you to figure out how many grams that it took, you would have to change the moles into grams, like we learned how to do already. Or if they wanted to know how many liters of a gas that represented, you'd have to change the moles into liters, which again, we've already learned how to do that too. All right, so let's try and go ahead and do this with an example. All right, so this example is a little bit more complicated than the one we just looked at, but really not much. This one says if I take 2 H2S plus 3 O2, it yields 2 SO2 and 3 H2O, or 2 H2O, sorry. Okay, so if you're looking at that, those numbers that are out in front, remember those numbers that are out in front, we generally will think of these coefficients as moles. But remember, they don't have to be just moles. As we saw in our last example, we could think of them as individual molecules, right? So one of the ways that we could interpret this is by molecules. Now, notice this doesn't say the number of molecules because things could be in atoms or in ions. So we just say particles, and then you have to determine whether you're looking at things that would be in molecules or not. Now, all of these are molecules, right? H2S is a group together. That's a molecule. O2, that's 2 O's together. That's a molecule. SO2 is in molecules. H2O is in molecules. These are all molecules. So if we were to interpret this in terms of molecules, those numbers out in front can stand for molecules. So the 2 out in front of H2S could tell you that if you took 2 molecules of that H2S plus 3 molecules of O2, you'll make 2 molecules of SO2 and 2 molecules of H2O. Okay. Again, is that really useful to us in real life? No, although technically that is one way that you could interpret that. What's much more useful is interpret this in terms of the number of moles. Now remember, those numbers that are out in front, the coefficients, they can stand for the number of moles. So 2 moles of H2S plus 3 moles of O2 would yield 2 moles of SO2 and 2 moles of H2O. Right? That's what our balanced chemical equation is telling us. If we actually went out and took 2 moles of H2S and 3 moles of O2, we should be able to make 2 moles of SO2 and 2 moles of H2O. Once again, how useful is that to us in real life? If we had to do this reaction for real, that's not very useful, because moles are not something that we can actually measure. But you can measure things like, for instance, grams. So maybe it's going to ask you mass. Interpret this in terms of mass. Now, here's where you need to do a little bit of thinking. Remember, the numbers, the coefficients up at the top there, do not stand for grams. They stand for moles or possibly even molecules, but not grams. So you would have to convert each of these, right? So the 2 moles of H2S would need to be converted into how many grams that is. And the same thing with the 3 moles of O2 here, okay? And the 2 moles of SO2 and the 2 moles of H2O would each have to be converted into grams. Now those are really easy to do because you'll just have to figure out how much does H2S weigh on the periodic table, multiply by 2. How much does O2 weigh on the periodic table, multiply by 3. And keep doing that all the way across. So I'm going to give you a moment. In fact, you probably just need to pause this for a moment. I want you to take your periodic table and your calculator and your paper, and I want you to figure out how many grams does 2 moles of H2S weigh, how many grams does 3 moles of O2 weigh, and do that for all 4 of these. Figure out how many grams they are. You can do a little rounding. You don't have to use every decimal on the periodic table, but go ahead and figure out how many grams that would be, and then come back and I'll show you the answer. Okay. So you've paused, you've tried to do this on your own paper. Now let's come back and look at what the answer would actually be, right? And it would look something like this. Now again, I kind of rounded things off a little bit, so you should be pretty close to these numbers if you did it right. So how did I get 68.2 grams for H2S? Well, I went on the periodic table, right? And I looked up H, which weighs about 1 gram, but there's 2 of them, right? So I have 2 grams from the H. And then the S here, right? If you look up sulfur on the periodic table, what is it, like 34.5 or something like that? Okay. So you'd have to go through and say, okay, this is like 30, it's not even 34, right? Is it 35, 36 or something like that? Anyways, so you would add up H2S, but then you'd have to multiply that whole thing by 2. That's how you get 68.2. Okay. If you go on the periodic table for O weighs around 16, except that there are 2 of them. So you have to multiply this by 2. So that tells you that O2 weighs 32 grams. Except that you also have 3 moles of it. So then you have to multiply that by 3. 3 times 32 tells you 96. That's where we get the 96 from. And then we did the same thing for the SO2 and for the H2O. And then when you're done, you can make sure that this works, because remember, law of conservation of mass says that these 2 grams together have to equal all of the products together, right? They all have to add up. 68.2 plus 96, what is that, 164.2? And 128.2 plus 36 is 164.2. So either way, it tells you that this is right. So when you're interpreting a balanced chemical equation, remember, the numbers that are out in front, the coefficients that are out in front, generally mean moles, although they could mean molecules or whatever particles they come in. And then if you want to think of these as grams, you'll have to convert them using the periodic table. Or if you wanted to think of these as liters, if these were gases, you could think of these as liters, and you'd have to convert them using the 22.4 conversion factor. Right? Okay. Last thing that we're going to do here is we're going to talk about how to use that interpretation to solve different problems using a chemical equation. So if you're given a balanced chemical equation, you now know that those coefficients in front in the balanced chemical equation stand for moles. That also means you know what the mole ratio is between each of those substances in that balanced chemical equation. Here's what I mean by that. Let's go back to this simple one from before. If you take a mole of nitrogen and 3 moles of hydrogen and you mix them together, this says that we should make 2 moles of ammonia when we're done. Okay? So, according to this balanced equation, it says that if I take 1 mole, remember there's a 1 that's right here, even though we don't see it. If you take 1 mole of N2 and 3 moles of H2, I make 2 moles of NH3. Now, that tells me that every time I take N2 and H2 together, I'm going to make some ammonia, but only in this ratio. So what if I was really interested in making 4 moles of NH3? What if I wanted to make 4 moles of NH3? Well, 4 is double of 2. So if I want to make double the product, I would have to use double of the reactants, right? So I'd have to use 6 moles of H2 and 2 moles of N2. And a 2 to 6 to 4 ratio is the same thing as a 1 to 3 to 2 ratio, right? If you were to reduce it, as long as the ratios stay the same, you can convert those numbers into any other numbers you want to. The mole ratios are the important part. This always has to stay a 1 to 3 to 2 ratio. So when we write out mole ratios, we need to write them out as conversion factors because we're going to end up using them to do something important later on. So let's start with the mole ratio between nitrogen and hydrogen. So if you look back at the original balanced equation right above us here, and I'm going to erase all of this stuff that I wrote out here. So if you look up here at these balanced chemical equation that we have up here, we notice that there is a 1 in front of the N2 and there's a 3 in front of the H2. So the mole ratio between nitrogen and hydrogen is that there is 1 mole of nitrogen for every 3 moles of hydrogen. So I write it as nitrogen over hydrogen. Okay, that's our 1 to 3 mole ratio. So when we write mole ratios, we're going to write them in these conversion factor forms, like a fraction. All right, so here's the same balanced equation. Don't forget it, but I'm going to move on to the next slide, and you're not going to see it anymore. So if you need to write it down, you can. We're going to use this balanced equation again. N2 plus 3H2 yields 2NH3. This time, what's the ratio between nitrogen and ammonia? Well, according to our balanced equation, I had 1 in front of the nitrogen, and I had 2 in front of the ammonia. So 1 mole of nitrogen, right, is 2 moles of ammonia. So it's a 1 to 2 ratio. Every time I use 1 mole of nitrogen, assuming I had plenty of hydrogen to go with it, then I would make 2 moles of ammonia. And then finally, I want you guys to try this one. Right? On your paper, I want you to write what's the mole ratio between hydrogen and ammonia. And again, if you want to pause this, or if you need to rewind and go look back at that equation again, you can do that. But I want you to try this on your own on your paper. Okay, so you've already written this down. Hopefully, if you didn't, pause and do that. Right, here's the answer. Again, In the balanced equation, it had a 3 in front of the H2, it had a 2 in front of the NH3, so it's a 3-to-2 ratio. And that's how we write it. Okay? All right, so at this point, you know how to look at a balanced equation and interpret it. And you know that the coefficients in front stand for moles, but if you wanted to convert them into grams or liters, you also know how to do that from back in chapter 10. So you need to, after writing these notes down, you need to start working on the problems that I have posted for chapter 12 so that you can go through and get those worked on. And then when we come back again and do some more notes in a couple of days here, then you'll have those done, right? The problems you can do done, and then we'll move on to the next part. In the next part, we're going to learn how to use these mole ratios to solve problems. And then we'll finally end up on Friday going over the last part of chapter 12. Okay? Alrighty.